y'all, welcome to Miss Clarke's chemistry class. We are on the 5th lesson of our series of lessons on redox reactions. In the previous lesson, we learned that chemistry can be used to generate electricity. Now we need to learn how to calculate how much electricity. We need to calculate the voltage. Guess what? You're going to need a calculator, so go get something to write with, your periodic table and your calculator, and let's get started. But let's remember a few things first. We're mostly going to talk about galvanic cells. Also, we remember that oxidation is losing electrons, and we remember that reduction is where we gain electrons, and that at oxidation this is happening at the anode, and reduction this is happening at the cathode. But I most wanted you to remember galvanic cells are spontaneous. That is going to be really important when we're trying to figure this out. So to figure out this voltage, we need to use this chart, and this chart's called a standard reduction potential chart. Now, of course, this is in an aqueous solution at 25 degrees Celsius. I'm not that worried about that information. What I do need to bring to your attention that this is for reductions only. So if we find our reduction equation here, we match that up with some number here, that's our value for reduction. But let's say that we're needing an oxidation. All you have to do is flip the sign. So for example, the reduction of fluorine, I'm looking at that very first one. It says F2 plus 2 electrons. If I'm reducing fluorine, that is giving me a 2.87 volts. But if I am going to flip this and get the oxidation of fluorine, all I have to do is flip the sign. I'm going to give it a negative instead. To read this chart, make sure you're realizing to use the number as is, that's when it's a reduction. If you're looking at this chart for an oxidation, flip the sign. Remember, we're trying to create a galvanic cell, one that's spontaneous. And for it to be spontaneous, it needs a positive voltage. And we're going to have to add the voltage between the oxidation half and the reduction half. So you're going to have the volts from oxidation plus the volts from the reduction. And we want this to be a positive voltage. If it's a positive voltage, then that means this is a spontaneous cell. That means it's galvanic, and that is our point. That's what we're trying to look for. Let's look at some examples on how to read this chart. Okay, so I wanted us to kind of play around with this a little bit. So I'm giving us 2 electrodes, aluminum and silver, and their aqueous solutions. Now again, this chart is showing reductions. So let's show when we reduce aluminum, let's see what the number is. So if we're looking at this chart and we're looking for aluminum, here it is way down here, aluminum, negative 1.66. When we are reducing silver, let's look and see what that value is. Silver's here, we get 0.8, positive 0.8. We're gonna have to flip one of these numbers because right now we have reduction. We're looking for the voltage of our redox. So we're gonna have to have 1 part reduction, 1 part oxidation. So we're going to have to flip one of these numbers. And remember, we're adding these numbers and we want to get a positive sum. So would we want to flip aluminum or would we want to flip silver? I'm hoping that you're noticing that we're going to want to flip aluminum. We want for aluminum to be oxidized so we can use that positive 1.66. And then we're going to reduce the silver. That's going to leave that the 0.80. That's how we're going to get the biggest charge. Sometimes you get to choose. Do you want this part of the reaction on the anode? Do you want that part of the reaction on the anode? And remember, you always want the oxidation on the anode. You might have to adjust which reactant is going to be the best place for the oxidation to make sure you're having a spontaneous cell. If this doesn't make any sense, just keep bearing with me and then think back through this when we get done. Here we were choosing. Oftentimes you will not get to choose. And the only reason why I was wanting us to choose was so that we could play around with this chart, realize oxidations are going to be the opposite charge. And that sometimes you can choose which one is going to be oxidized and which one's going to be reduced to give you the best cell. Let's look at an example. Here, we can't choose which one's being oxidized and which one's being reduced. It's already being done for us. So let's go ahead and figure out which part's being oxidized, which part's being reduced. Okay, so copper is free, so it's a 0. Here's oxygen is a 2, Silver's always a 1. But remember, sulfate, SO4, is a 2. So if we're trying to figure out sulfur, we've got -8. We want the total to be -2. Sulfur has to be a +6. That gets sulfate as a -2. And then if we have 2 silvers +1, that should work out good. So we've got 2 +6, that's 8, -8, that's 0, that's good. So if we come over here, I'm gonna go ahead and put that 0 on silver. Oxygen is a -2. There's that sulfate again. That's going to be 6. So if we have this +6 and we have this -8, that's going to leave copper +2. So copper is going from a 0 to a +2. That means we've lost 2 electrons. That means it's being oxidized. And then silver is going from a +1 to a 0. That means it's gaining 1 electron and it's being reduced. So we just said that copper is being oxidized. So let's write that. Copper. You know, instead of writing this SO4, I'm just going to write the ion that it stands for because that's going to make it easier for us to look it up on the chart. Okay, so copper went to a +2, right? Copper was a +2 up here. And that means we lost those 2 electrons. Let's look at silver. Let's just use the ion again. Silver +1, right? That was a +1 right here. And it's just going to silver. And we need those electrons, 1 electron. So here's our half reactions, oxidized, reduction. So when we look at copper, we need to make sure we're using the one with 2 electrons, and we're gonna have to flip its sign because it's being oxidized. Okay, I brought over my work. I'm covering part of my reaction with my chart, but I wanted you to be able to see it. Okay, so let's find copper with 2 electrons. Here we go, 0.34. But remember, it's being oxidized. So copper is really going to be -0.34. Silver, let's find silver. Here it is, 0.8, and it's being reduced, so we'll leave it the way it is. And that was a +0.8. So if we add these together, what is that, 46? +46. Let me do that better. I gotta do it backwards, y'all. Yeah. +46. That's a positive cell, so that is spontaneous. Let's find the charge of one more, but this time I just showed you a picture. Okay, so things that we need to notice before we can go on is right here, anode. Zinc is at the anode. That means zinc is being oxidized. So if we were going zinc, it's being oxidized, so it's losing those 2 electrons. We know it's 2, right there, 2, oxidized. And then we know copper is being reduced. Okay, so zinc is being oxidized, copper is being reduced. Let's go look at our chart. Okay, and I wanted to bring over what we had said. So let's find zinc. Let's find zinc, and it's going to lose 2 electrons. Here's zinc. There's its 2 electrons. -0.76. But remember, it's being oxidized, so we got to change that sign. So instead of -0.76, we're going to have +0.76 for the oxidation part. Now let's look for the reduction. Reduction is copper with 2 electrons. Here it is, 0.34. We're going to use that number as is. And so when we add those together, we get plus 0.80. This is a good spontaneous cell. If we get a negative, it is not a spontaneous cell. Therefore, it's not galvanic. It is electrolytic, and it needs energy added in to make it run. I don't know about y'all, but I think it's pretty cool that chemistry can generate electricity. And now you have a better understanding of how to do the calculations to figure out just how much electricity a redox reaction can generate. I've got one more video left in this series, and I'm just going to put this all together and we're going to do practice problems. These are the things that I would expect for my students to be able to do in class. So meet me back for that one. Until next time, bye y'all.